Okay, today we'll talk about convergence of various algorithms. Picture is of the secant method. That'll be one of the ones that we will discuss in this video. So we want to look at methods that produce a convergent subsequence, at least in a range. And we want to predict the computational order of convergence, and we'll look at methods like the fixed point iteration method, the bisection method, Newton-Raphson method, secant method. In a subsequent video, we will talk about Muller's missing method and Muller's original method, but not in this video. So we will not study the conditions that guarantee convergence. We will not review the actual algorithms in this video. It is assumed that you have seen previous videos on these methods. This video will assume knowledge of calculus and Taylor's theorem. So fixed point iteration, x sub n plus 1 is defined as f of x sub n. That defines the process. And the fixed point is r. R is the unique point that f of r is equal to r. Now we can define xi of n to be the difference between r and the estimate. It's sort of an error term. We'll use this notation throughout. Xi of n plus 1 is xi of n, x sub n plus 1 minus r. Now we can use Taylor's theorem to say something about xi of n plus 1. It's roughly equal to the derivative of f times xi of n. That means that the ratio of xi of n plus 1 over xi of n is approaching a constant, and the constant is the derivative at the fixed point. It's important that f prime be less than 1. So taking logs, we can find a pattern in the log of the error terms. The ratio goes to 1. That means it's linear convergence. And xi of n plus k is roughly equal to k times alpha plus z of n. So you can predict how long it will take to get the desired precision. Now with the bisection method, we're going to not talk about the mechanism for determining whether r is in an interval. We'll just know by looking at it whether it is or it isn't. But by definition, r is going to be in each of these intervals. And the difference between the interval, the high and the low estimate, is going down by a factor of 2. That defines a bisection method. We cut the interval in half each time. And we'll use the midpoint as the estimate of x. So x is equal to the root r plus xi of n. So xi of n is kind of random. It's kind of hard to know exactly what it is, but we know that the maximum value is going to be half the distance between, half the interval distance. And over time, these error terms are going down by a factor of 2. Maybe not each time, but if you look at enough time periods, it will average going down by a factor of 2. So when we take logs, we'll be able to see a pattern in these errors. And the pattern is, well, that the ratio of the errors is approaching 1, it's linear convergence, and z of n plus k is equal to k times alpha times z of n, just like with the fixed point iteration method. Now with Newton-Raphson method, the convergence will be very different. We have a law of motion for x of n plus 1, and we define the xi of n term in the same way we did before, as the difference between the root and the estimate. And now we'll use Taylor's theorem to get an estimate that we can plug in to find xi of n plus 1. Note that g of r is equal to 0 by definition of r. And we have a Taylor's theorem expansion for g prime as well. We'll plug that into the formula. We'll get some nice cancellation in the numerator. The xi n g prime term is going to cancel. It cancels not just in Newton's method, but Secant's method, and just about anybody's method that you can think of. And when we combine terms, we'll get that xi of n plus 1 is g double prime xi of n squared over 2g prime. And so the ratio of xi n plus 1 over xi n squared is approaching a constant. So when we take logs, we'll see that the ratio of the log of these error terms is 2. That means it's quadratic convergence. And convergence is actually really fast with Newton's method. Now let's look at the secant method, which has a lot of similarity with Newton's method. The law of motion for x of n is very similar, except now we use a numeric derivative instead of the actual derivative. And that's going to bring in these lagged terms. That makes the computation for the error terms a little bit more interesting. So we use the Taylor's theorem just as before, but when we plug it in, we realize because we have these lag terms, we get these xi of n minus xi of n minus 1 kind of terms. And this second term factors, we can factor out a xi of n minus xi of n minus 1 term out of every term in the sequence. And that's the denominator, is xi n minus xi of n minus 1. So we get a nice rule for the slope term. It's g prime plus g double prime times the average of xi n and xi n minus 1, plus some other terms. Now when we use the law of motion for xi n plus 1, we'll get some nice cancellations in the numerator. The g prime xi of n term cancels. It cancels in everybody's method, but there's actually more cancellations here in the numerator. All we get is 1/2 g double prime times the product of xi of n and xi n minus 1. The denominator converges to g prime, so the ratio of xi n plus 1 over xi n times xi of n minus 1 in the denominator approaches a constant. Taking logs, we'll get a very interesting, simple process. we get that Zn plus Zn plus 1 equals Zn plus Zn minus 1 plus a constant. It looks like a Fibonacci type sequence. The constant doesn't really matter very much because these terms get to be so big. Assume that the ratio of logs of the errors approaches a steady state. So assume that the ratio is beta. Let's solve for beta. We'll plug in for that rule. This is Cn of n plus 1 in the numerator, and the denominator is the rule for Zn plus 1. And we're going to divide through by d beta to the n minus 2 and let n approach infinity, and we get the steady state is that beta squared over beta plus 1 is equal to 1, or beta squared is equal to beta plus 1. And the solution to that, we know, that's the golden ratio, 1.618, which is not quite quadratic. It's slower, it takes more steps for this to converge, but it's still pretty fast. Now, we'll do a little calculation here. We always do a calculation. We always go to the spreadsheet. And we're going to use Fibonacci's method to see if we can solve the equation beta squared equals beta plus 1. So what we'll do is, well, that's I is just a counter. So we're going to count the steps. In the Fibonacci process, we say 1 and 1, and then the next term is the sum of the previous two terms. And we bring that down, and we'll get this iconic Fibonacci type sequence. And we'll calculate the ratio of terms. This is what we assume is going to get close to 1.618. And like any sequence, we want to calculate the difference between adjacent terms to see how close we are to 0, and we want to compute the ratio of convergence to see if it's converging quickly to the solution, how quickly it is. So phi, that's the golden ratio. We know the answer. It's 1/2 the square root of 5 plus 1. The true rate of convergence turns out to be 2 minus phi. We'll take 60, maybe 70 terms and see if it converges. And yeah, it converged after maybe 40 some odd terms. So let's use the ratio d, see how close that is. Yeah, it's all the digits. And then we'll compare the estimated return rate of convergence to the true. It's not quite as accurate. It never gets to be more than 10 digits, but that's good enough for what we're trying to do. Now let's try different values of the Fibonacci numbers. Let's try 1 and 10, for example. It doesn't make any difference. We get the same estimates every time. So okay, it's time to close the spreadsheet. Thank you.